Hello, everyone. It's Mr. Chappa. I'm going to try to make more videos specifically for the support assignments, the 0314 assignments. Not necessarily an instructional video per se, but more of a let's walk through this assignment together. And we'll leave the instructional videos for the Math 1314 class. So for this week, in week 6, we are going to, let me find the screen here. Now, you can't see, well, as of the creation of this video, this module has not been published yet, but by the time you watch this, clearly it will be published because you'll have clicked on this link, Solving Multivariable Equations video. But I want to go ahead and click the Solving Multivariables Equation 0314 homework. This homework, the skills in it will help you with the finding of an inverse function. As you can tell further down in the first batch of 1314 videos, finding the inverse of a function, videos 6 and 7 in this series. So this video specifically focuses on helping with the algebraic process that's involved in finding an inverse function. So we're going to click on the homework, and we're going to go ahead and open it in a new window. Not all the homeworks have the open in a new window setting. I'm trying to catch more of them so that when you open the homework, it's not trapped in that little bitty box in the middle of the page. And just a reminder, you can always click on My Lab and Mastering. Go back to, let's go back to the student view here. And when you click on My Lab and Mastering, you can go in and click Assignments. And you can do the homework there, because if you do it there, it will pop it open in its own window. But for now, let's go ahead and just take a look at this. We're going to go through these 10 questions because these, like I said, these are skills that are going to be necessary for finding the inverse of a function. All of these equations are going to be the same. They're going to have multiple variables and going to be asked to solve for a specific one. For example, solve the formula for the specified variable, n equals y times k, and they want you to solve for y. Well, in general, when you're solving an equation for a variable, let's see, what was it? It was n equals yk, and we're solving that for y. All right, so come on, text box, go. All right, so let's solve n equals yk for y. All right, whenever you're solving for a variable, the gist of it is, why is it not by itself? And then fix that. For example, this y is not by itself. This y right, come on. This y right here is not by itself because it has that k attached to it. So our move should be focused towards getting rid of that k. Well, to get rid of a variable or a number that's attached to another variable, you should ask yourself 2 questions. How's the variable attached? And what's the opposite of that? In this case, the k is multiplied by the y, and we need to get rid of the k. Since k is multiplied, we divide both sides by k. And the result of that is that the k's cancel. Technically, k divided by k is 1. Then the right side becomes 1 times y, which is equal to y. But the net result is the k's cancel. And what we're left with on the other side is what y is equal to. So we end up with y equals n over k. It's a pretty easy move, but the biggest mistake people make on this type of equation is dividing by the wrong letter or writing their fraction upside down. But if you show the move that you want to do for the reason, I want to divide both sides by k to get the y by itself, and be careful to do it on both sides correctly, then the other side of the equation should come up with the correct expression. All right, so we need n over k. Let's go back to here. Let's put it in n over k, and you can just hit the slash button on the keyboard to set up a fraction. We'll check that. Hooray. Let's see, number 2, solve for the specified variable. C equals 1/2 f times m for f. C equals 1/2 f times m. C equals 1/2 f times m. C equals 1/2 f times m, and we want to solve this for f. So let's highlight the f real quick. Now, unlike the previous one, there are 2 reasons this f isn't by itself. It's multiplied by 1/2 on the left, and it's multiplied by m on the right. Technically, I know how to get rid of things that are multiplied. I divide both sides. However, I chose this problem because I want to focus on the fact that we're getting rid of the fraction. In general, if you're getting rid of a fraction that's multiplied, you can multiply both sides of the equation by its denominator. In this case, I can multiply both sides of this equation by 2. The result is we get 2 times 1/2, which is equal to 1, but essentially the 2 and the 2 that I multiplied by and the 2 in denominator cancel, leaving just a 1. And if that 1 were any other number, we'd have to keep up with it, but it's just 1. And since we're multiplying by 1, we can just ignore it now. We have 2 times c is equal to the 2 and the 1/2 cancel, f times m. And keep in mind that we're solving for f. Then all I have to do is get rid of the m. And the m is multiplied, so we just divide both sides by the thing that's multiplied. Cancels the m's, and we are left with f equals 2c on top and m on the bottom. All right, so that's not too bad. But again, the focal point on this question was, what do I do with the 1/2? And my reply would be get rid of it as soon as possible. All right, so we get f equals 2c over m. Now, if you're thinking, I know this, then I invite you to pause the video, go try the homework right now. Okay, I'm here to support you. But if you've already got this, then you've got this. Even if you think you might have it, but you're not sure, try some of the problems and see if you can do them. See how far you can push yourself mentally. But in terms of review purposes for down the road, you want to write stuff down, make good notes. Think of notes as talking to yourself in the future. Hey, future me, I want you to know how to do this thing. And then future you looks back on it and said, hey, I forgot how to do that thing in the past. Thanks, past me, for reminding me how to do it. Question 3, solve the following formula for this. Okay, W equals HRU for H. We're going to solve W equals HRU for H. All right, W equals HRU. And don't know why some of these letters are capital and some of them are not. We're going to solve this for H. Let's highlight the H to help us focus. And so why did I choose this question to be on your assignment? Because we're getting rid of 2 things that are multiplied simultaneously. The H is being multiplied by R and it's being multiplied by U. Now we have 1 or 2 options. Option number 1 is to get rid of one of the things we don't want at a time. In this case, we don't want the R and the U. If we were to do that, let me show you what would happen if we just got rid of the H first. We would have W over R equals HU. But the problem with getting rid of one of those things is the next move. I would still be dividing both sides to get the H by itself, except this time I divide by U. But what are you going to do on the left side? The left side's now a fraction. Are you going to put it on top of a U? And that's a situation that we can get out of. But the better question is, can we avoid getting into this complex fraction over here? Complex fraction being a fraction with a fraction inside of it. And the answer is we can't avoid it if we'd made a different decision at the beginning. If you want to know how to take this and clean it up, just send me a text or a message and I'll make a short video for you. But I want to talk about making the better decision at the beginning. At the beginning, we had decided, let's divide both sides by R. However, when I see an equation like this one with 2 things multiplied that I want to get rid of, like R times U, I look at this R times U as a single part of a 2-part multiplication problem. This is H times RU. And by looking at that RU as a single factor made up of 2 factors in its own right, I can get rid of them simultaneously by simply dividing both sides by RU. The rule for canceling in a fraction is simple. If you're part of a multiplication problem on the top, like up here, and part of a multiplication on the bottom, like we are down here, and you match, like the R's match and like the U's match, then I can cancel you. Again, if you're part of a multiplication problem on the top and part of a multiplication problem on the bottom, and you match, I can cancel you. So I could just cancel this R and this U collectively, or I can either think of it as canceling 2 things back to back or one big thing on both sides. Either way, you get the H by itself, and we have W over RU. All right, let's go put that in. W over RU. Now, if you're watching this video and you haven't opened the homework yet, I strongly recommend pausing the video, open your homework, and following along. Speaking of pausing the video, I got to check on something. I shall be right back. Okay, pause, and resume. All right, solve the following for K. U equals 2 pi K. Well, to be honest with you, this question is just like the previous one. It's 1 thing on the left equals 3 things being multiplied on the right. This is 1 thing on the left equal to the product of 3 things on the right. We're solving for K. Well, U equals 2 times 2 pi K. Well, let's talk this one out. If I'm solving for K, which is embedded in a multiplication problem, I simply have to divide the things that are multiplied in front of k. So I have to divide both sides by 2 and pi. I can do them separately, but I'd rather do them collectively. If we divide both sides by 2 pi, it will look something like this. Go back to the whiteboard, please. Thank you. U equals 2 pi k. Again, I'm solving for k, so let's highlight that for emphasis. And the only reason it's not by itself is because it's got a big chunky thing multiplied in front of it, 2 pi. If I divide both sides by 2 pi, it sets up the fraction construct that allows us to cancel. Remember, what that means is multiplication problem on the top, multiplication on the problem on the bottom. We have matching factors. The 2's and the pi's cancel, either separately or collectively. Regardless, the only thing left is the k, and we end up getting k equals u over 2 pi. Something I take for granted that I should pause and mention, you can reverse the order of an equation at no cost. Because specifically, you'll notice that the k was originally on the right side of the equation, and I just magically wrote it on the left. And then the expression that I got by its when I saw for the k, the u equals, the u over 2 pi, I wrote that on the right side. It's perfectly acceptable to reverse the order of an equation. It's something called the symmetric property of equality, but it makes sense if you think about it. Like if we talk in terms of ages, if my age equals yours, then your age equals mine. We're simply reversing the subject and the object of that sentence, but it's an equality, so it's okay. And some people say, but you moved it to the other side. Aren't you supposed to change its sign? Well, yes, and technically they both did, but then I multiply both sides by -1 and all the signs go back to the way they were. So you can reverse the order of an equation at no cost, not an inequality, but at an equation. All right, so let's put it in that answer that I think many of you probably could have gotten at this point just by looking at the problem and saying, well, I'll have to take the u and divide it by 2 pi. I was wondering if typing pi would work. It did not. Let me check it and see what it says. Whoa, okay, I learned something. It will accept pi for the pi symbol. I'm assuming you can also click a button. Let's look at question 5. Okay, solve for n. We have a equals nc squared. All right, well, this is just n times something. It just so happens that the things that it's multiplied has a square on it, but that's irrelevant because the thing that's attached to the c is attached by multiplication. The fact that that thing is a c squared is completely irrelevant. So what would we do to both sides to get the n by itself? Well, we would divide both sides by the c squared. And if we divided both sides by the c squared, then the a would be on top and then the c squared would be on the bottom. Don't know if you know this, but if you hit Shift-6 on your keyboard, it shows a caret symbol that looks like an arrow pointing up. If you hit Shift-6, it will set up an exponent, and then you can type it in instead of clicking the little exponent button, which would also work. All right, it's a piece of cake. Let's keep going until we find something that's a little trickier. That didn't take long. Solve the formula for V equals C plus VF. I believe this is the first one we've had that involves any addition or subtraction. And it does also involve multiplication because we have V times F. Whenever you have an equation with multiple operations in it, such as addition and multiplication, and you're solving that equation for something, there's a particular order in which you should solve for. B equals C plus VF. B equals C plus VF. I can type this one. B equals C plus VF. And I believe we were solving for, what were we solving for? We're solving for V. Okay, let's go ahead and put solve for V here. So let's think about this for a second. Let's highlight the thing we're solving for, the V. Now, to get the V by itself, I have two things to get rid of. I got to get rid of the C, which is added, and I got to get rid of the F, which is multiplied. But which one do I get rid of first? Well, the answer to that lies in doing something backwards the way you would normally do. I'm sure most of you have heard of PEMDAS, the order of operations. Please excuse my dear Aunt Sally, which is an acronym for, or a mnemonic device for parentheses, exponent, multiplication, division, addition, and subtraction. It's the order that you do a math problem in. But we're not really doing a math problem, we're undoing a math problem. This would be used for something like evaluate 5 squared plus 4 times 3. Well, there's no parentheses, so I would do the square first, the exponent. 5 squared, of course, is 25. And then on the next layer, the MD means multiply and divide in order from left to right. So I do 4 times 3, which is 12. And then the last thing I do is add 25 plus 12 is 37. But that's how you do arithmetic. It's how you evaluate an expression. When you're solving an equation, you're basically undoing an expression that was already done to figure out one of its missing pieces. And as a consequence, when you're solving an equation that has multiple operations in it, you have to go back up the order of operations. Over here where it says C plus VF, if I knew what C and V and F were equal to, I would multiply first and then I would add last. So to undo that, I have to unadd. So we're going to take care of the C first. The C is added, and so we're going to subtract C from both sides, which will cancel the C's on the right. Actually, C minus C is 0, but 0 plus anything is itself, so it's a good number to add with. On the left side, we get B minus C, which I can't answer. And on the right side, we have V times F. Keeping in mind that we're solving for the V, which is now a little bit more by itself. Now I just have to get rid of the F, which is multiplied. So we'll divide both sides by F. But be careful. When you divide one side of an equation by something, but that side is an addition or a subtraction problem, that entire problem gets divided. So the entire subtraction problem, B minus C, is going to get divided by F. And that will leave a fraction with B minus C on top and F on the bottom. Again, I may be making more out of this than necessary. This may be something that some of you could solve without the need for my intervention. But again, in order, we would subtract C from both sides. So the C would get subtracted from the B. Then we would divide both sides by F. In case you're wondering what I did, to get this B minus C in the top of a fraction, I can highlight it, click the fraction, and it will default it to the numerator. All right. 4 left. We're going to go through all of them. Okay, well, this has got all kinds of stuff. It's got a fraction, it's got a multiplication problem, and it's got an addition problem. And it's got parentheses. So we're going to have to figure out the correct order in which to get rid of all this stuff. Solve for S. C equals 1/4 times M times the quantity S plus K. All right. So we're going to solve C equals 1/4 times M times the quantity S plus K. And we were solving that for S. All right. If we're going to solve for S, we actually have some options now. Because where is that S located? Well, there's a couple of ways to answer that, but primarily it's inside of an addition problem. But that addition problem is embedded inside of a multiplication problem. So we got a lot of layers to peel off here. But first and foremost, I don't like that 1/4. And I like to fix it first. Do you remember what I said you could do to both sides to get rid of a fraction? You can multiply both sides by the denominator. Now, this is not the only first move that you can do, but it's the first move that I would recommend because doing it will allow us to cancel the fraction, which always makes the problem easier than it used to be. Let's keep in mind that we are solving for S. I think I accidentally undid a move and it undid the highlight on the S. All right, so now we're continuing to get the S by itself. There's a couple of options that we can do here. Number one is we can get rid of the parentheses by distributing the M. In fact, why don't we do that? Because I think a lot of people's instincts here would be to distribute. There is another option that we can do, so I will get the other option. I'll demonstrate the other option in just a moment, but let me go ahead and get the question rewritten where we currently are. See the screen bouncing. It's because I'm touching some editing tools as I'm making this video. Okay, but let's go with the distributive property. Wrong color blue, wrong shade, or different, I should say. Let's go with the distributive property where we multiply the S and the K by M and get MS plus MK. 1 second, folks. I'm going to grab all this and move it up a little bit so I can have some more room. I've got a toolbar at the top of the screen, which is why I start writing in the middle. I don't think you can see the toolbar, though. Now my face is blocking something. There we go. All right. So after we distribute the M, and keeping in mind that we're solving for the S, this is a task. This is a task-oriented goal. So stay focused on the task of isolating the S. Now we're kind of in the same place we were in this previous example, where the V was embedded in a multiplication problem, which was embedded in an addition problem. This S right here on the left side on the bottom is embedded inside of a multiplication problem, which is embedded inside of a larger addition problem. So following the same protocol, we're going to get rid of the MK, which is added, and so we have to subtract it from both sides, which will cancel the plus MKs, leave 4C minus MK on one side and MS on the other. And again, keep it on focused on the fact that we're solving for S. We need to get rid of the M, which is multiplied, and you unmultiply by dividing things. Try that again. There we go. And we're dividing the left side by M, but the left side is a subtraction problem. So like we said back here, when you divide both sides and one is a subtraction problem, the entire problem goes in the numerator. So this entire problem goes over M, which gives us our first variation of the answer. S is equal to the following fraction: 4C minus MK on top, M on the bottom. Now, there may be a temptation to cancel these M's. This M on the top, this M on the bottom. Resist the temptation. Because remember what I said earlier back here, and I think on a previous example? The criteria for canceling in a fraction is simple. You have to be matching parts of multiplication problems, one on the top, one on the bottom. In here, the 2 pi's cancel because they matched. They were on both sides and they were all parts of multiplication problems. Just remember, a fraction is a division problem. You cancel things when opposites collide, and the opposite of dividing is multiplying. The pink M on the top of the fraction right here, let me draw an arrow pointing to it, right there, is part of a multiplication problem, but that multiplication problem is embedded inside of the subtraction problem. And as a consequence of being embedded inside the subtraction problem, nothing on top can cancel because everything on top is embedded in that subtraction problem, which means the pink highlighted M's will not cancel. And as a consequence, this would be, let me draw a box around it. This would be an acceptable answer. But that's if you had chosen to do the distributive property back up here. What if instead you had chosen to do something different? Because when you're solving for something, you're getting rid of things that are attached to it. When the S was embedded inside of the addition problem, S plus K, which was embedded inside a multiplication problem because it was multiplied by M in front, you might choose to distribute like we demonstrated already, or you might choose to get rid of the M altogether, because after all, we're trying to get the S by itself, and the M is in our way. The M is attached by multiplication, and we could divide both sides by M. That would cancel the M's. Now, the M on top of this one is cancelable because in the green box on the right side of the equal sign, it says M times something. That means that the M is embedded inside of a multiplication problem. This one down here right here was part of a multiplication problem that was embedded inside a subtraction problem, which nullified any chance of canceling. But we can cancel here, which we just did. All right, so what does that leave us? That leaves us 4C over M is equal to S plus K. Oh, now all I have to do to get the S by itself is unadd. In other words, undo the plus K, and we undo that with the minus K. That will get the S by itself because the K's will cancel on the right. But on the left side, we have a subtraction problem that we can't finish. 4C over M, then minus a K. There's nothing left to do there, but is that an acceptable answer? Or more importantly, is it the same as the previous answer that we got? And the answer is yes, if you completed the subtraction problem. You could complete the subtraction problem by getting a common denominator on the 2 fractions inside the green box on the bottom. The second part of the subtraction problem is just K, which is K over 1. And to make it have the correct denominator of M, we could multiply both sides of that fraction by M. So we'd have 4C over M minus NK over M, keep the common denominator, put the numerators together, and we end up getting this answer. So which of these answers is best? Whichever one you got to, and the homework should accept either one. Let's see which one I want to put in. I'm going to put in the, let me talk my way through this problem. We have the C, we multiply by 4 to get rid of the fraction. And then if we chose to divide by m to get rid of the times m, then we could do minus k to get rid of the plus k, and it should accept that. It would also accept the other answer that we got, the one that had one fraction, the one in the pink box down here. All right, just a few more. And hopefully you're getting something out of this. I'm going through this not just to show you how to get the answers. View an example can do that. I'm going through it to kind of get you inside the thought process to solving some of these equations. Number 8, solve for C. G equals n over C minus P. Well, notice where the C is embedded. It's inside of a subtraction problem, which is inside of a fraction. So we've got two major obstacles to overcome. G equals n over C minus P. All right, G equals n over C minus P. And I'm going to solve for C. This is a pretty tricky one, namely because the thing that we're solving for is currently inside a denominator. And how do we fix that? Well, you're never going to be able to solve for that C as long as it's in the denominator. So somehow we have to get it out of the denominator. And if we get rid of the fraction, then that would get it out of the denominator. So what can we do to get rid of the fraction? Well, keeping in mind that a fraction is just a multiplication problem, all we have to do is the opposite. And what is the opposite of excuse me. Let me try that again. I'm trying to make something happen here. It's not working. All right, let's try that one more time. We're trying to solve for C, which is inside of a division problem. It's inside the denominator. We're not going to be able to solve for C as long as it's in the denominator. To get it out of the denominator, we get rid of the entire fraction. And how do you get rid of a fraction? Well, keeping in mind that a fraction is just a division problem, the way you get rid of a division problem is by multiplying. We're going to multiply both sides of this by the denominator. Now, because the denominator is a subtraction problem, we need to put parentheses around it when we're multiplying by it. But if we multiply both sides by C minus P, then we are justified in canceling like that. And if you think I'm contradicting myself, because on the previous problem I said over here you can't cancel these m's because the one on top is embedded inside of a subtraction problem, every bit of that is true. I can subtract the C minus P's, however, because I'm not canceling pieces of the subtraction problem. I'm canceling the entire subtraction problem. So there's a subtle difference in canceling part of a problem versus canceling all of a problem. But continuing with the problem, that leaves C minus P times G equal to N. All right, well, the good news is we got the C out of the denominator, but now it's trapped inside of a multiplication problem inside of parentheses. So keeping in mind that we're solving for C, which I forgot my highlight back here, but that's okay. There's two reasons the C is not by itself now. It's inside of a multiplication problem, and it's part of a subtraction problem. Well, I'm in the same situation I was back here when I went in one of two directions. Do I distribute or do I get rid of the number in front? Let's get rid of the G, although I am justified in distributing the G. The G being outside the parentheses is further away from the C than the P is. And a good rule of thumb when you're solving an equation for something is if you're trying to decide what to get rid of, the further away it is from the letter you're solving for, the sooner you'll probably get rid of it. In this case, we could get rid of the G by dividing both sides by G, and that would give us C minus P is equal to N over G. And now we're just one move away from finishing. We can add P to both sides, or at least try to add P to both sides. That will cancel the minus P's. Didn't highlight my C's. I don't think that was super critical, but just to be consistent. And when we add P to both sides, that'll get the C by itself. That will get the C by itself. And we'll have N over G plus P. Had you chosen to distribute, I'm going to pick it up from here on the next page. Had you chosen to distribute, C minus P times G is equal to N, then you would have gotten CG minus PG is equal to N. Then you could add PG to both sides because remember, we're solving for C. Bring back my focus gimmick here. Then you could add PG to both sides because you're not getting rid of the P or the G. You're getting rid of the entire second half of the subtraction problem. That gives you CG equals N plus PG. And then to get the c by itself, again, we're solving for c. You can divide both sides by g and divide the entire right side by g. And you get c equals n plus pg over g, which doesn't look like the answer we got before. The answer we got before right here was n over g plus p. Not the same thing here. Remember when I said you can't cancel the g's? Because the g that I'm about to highlight in pink is embedded inside of this addition problem. Therefore, you cannot cancel it. There is a way to cancel part of an addition problem, but you can't do it while it's sitting inside of a fraction. The trick is to split the fraction into two parts by unadding, meaning that you keep the common denominator, but you give each numerator its own fraction. And at that point, the g on the top of the second fraction is now only part of a multiplication problem inside of that fraction, meaning that these g's are cancelable, meaning that you would end up getting n over g. Not sure what just happened there. Let's try to fix that. You would still get n over g at the beginning, but on the second one, the g's would cancel, leaving a plus p, which is the same answer we got over here. Which one's the best answer? That's a matter of opinion. I'm going to type in the one that you see here, the big fraction with n plus pg on the top. Although I'm not sure how long this video is, but I figured if I'm going through all of the homework, you're probably okay with it, or at least all of the 0314 homework. All right, so we had a fraction, and we had a n plus pg over g, I believe is what we had. We did. Nice work. All right. I think 9 and 10 are cut from the same cloth. Nope, they're not. I'm going to take the time to do them. Solve this mess for g. Big issue here, g is in two places. How do we overcome that? Well, hopefully you're made it to this part of the video, because what I'm about to show you right now is critical for at least one, if not two, of the homework questions in section 2.7 for math 1314. How to solve for a variable that shows up more than once in an equation. We're going to solve f equals 2gh plus 2gk for g. F equals 2gh, come on, plus 2gk for g. Okay. Text, please. Solve f equals 2gh plus 2gk for g. Make sure I copy the question correctly. Not switching over to the screen. I'm just clicking so I can see it, but you still see the whiteboard. 2g, that is correct. Okay. Now, there's a trick for solving for a variable that shows up multiple times within an equation, such as this g. And I'm actually going to type this as a how-to list. How to solve an equation for a variable that shows up more than once. It's kind of a long title, but I guess it's a good descriptive title. And can I fit it all on one line? I can almost do it. I could not do it. How to solve an equation for a variable. How to solve an equation. Let's try to find some way to make it. I don't think lowercasing is going to get it all on one line. Maybe. Nope. Well, I guess I'll just do this. I know this is an irrelevant something to worry about, but my OCD sometimes kicks in and it won't let me stop until I fix the problem. All right. So number one, I'll keep this on 24-point font. Guess I'll just go in here then. All right. Number one, get all terms with that variable on one side of the equation. And this one, it's already done. In other words, everything with a g is already on the same side. Now, what this also implies is get all other terms on the other side of the equation. In fact, we're going to make this step 2. What you're doing here is what I call segregating a variable. Segregating simply meaning get everything with a letter, one letter over here, and if you don't have the letter, you get over there. So all my g terms on one side, all my non-g terms on the other side. In this case, all the g terms are already on one side, and all the non-g terms are already on the other side. Number 3, factor out the common variable. So if you'll notice on the right side of this equation, both halves of it both the 2GH and the 2GK have a G in common. So we can factor out the G as a common factor. That's not the greatest common factor because there's also a 2 in common, but I'm solving for the G, so the G is the only thing that I want to factor out. So in this problem, that means we're going to, here we're going to factor out G. And that's how you spell factor. We're going to factor out G. And in this case, we're factoring out G because it's what it's solving for. And that will leave 2H plus 2K in parentheses on the right side with the G. All right, so what is the advantage to getting all the G terms on one side, non-G terms on the other, and factoring out the G? The answer is simple. How many G's are in the problem now? There's only one G in the problem. That's great because our goal is to get the G by itself. And now that it's down to one G, we can do that. Divide to isolate that variable. Factoring just basically turns something back into a multiplication problem. And so we can view it as such. And let me write this a little bit larger. Let me write this a little bit larger. We have F, not that thick. Come on. We have F equals G times 2H plus 2K. Now, some people will want to distribute the G, but that'll take us right back where we were. We're solving for G. The G is not by itself. The only reason it's not by itself is because it is currently being multiplied by all of this. Well, I know how to unmultiply things. I divide. The fact that the thing I'm dividing by is an addition problem inside parentheses is irrelevant. You cannot cancel parts of addition problems, but you can cancel all of them. So all of the addition problem is gone, and what we're left with is G equals F over 2H plus 2K. Now, you might be savvy enough to be able to look at this problem, have this flow in mind, and solve this without doing it in your head completely. It's not an impossible skill. It's a learnable skill, but I would always write it down so that you can look at it later and go, oh yeah, that's how I did that problem. I'm not concerned about answers. I am, but I'm way more concerned about processes. How do I get from the beginning to the end? Because as a skill solving technique, how to get from the beginning to the end is pretty critical. Number 10, solve for F. Well, where's the F? It's in the bottom of a fraction. So we're going to have to fix that. In fact, there are more fractions here than I care for. So I think what I'm going to do when I attack this problem is get rid of all the fractions right away. We're solving for F, and the equation is 1 over P plus 1 over N equals 1 over F. And we're solving for the F. Now, there's a couple of ways to do this. One involves doing the addition problem on the left side first. The other one deals with getting rid of all the fractions. What would you rather do? Keep two fractions and add them, or get rid of the fractions? Most people would want to get rid of the fractions. But here's the problem. If I'm going to get rid of one fraction, I might as well get rid of them all. So what can I do to both sides to get rid of all the fractions? Well, to get rid of a fraction, I multiply by its denominator. So like if I wanted to get rid of the P in the denominator, I'd multiply both sides by P. But that won't get rid of the N. I would have to multiply by N. But neither of those will get rid of the F, so I have to multiply both sides by F. A fairly common equation solving strategy is when you're solving an equation with lots of fractions, you should probably get rid of them as soon as possible. And you can always achieve that by multiplying both sides by all the denominators. Now, sometimes that's not the least common denominator, but in this case it is. I'm going to go ahead and distribute the P and F on the right side of the equation so that all three fractions have their own P and Fs. And what happens? Well, I can do some canceling. On each fraction, the thing that I multiply that matches the denominator cancels. The P's, the N's, and the F's. What does that leave us with? Well, in the first fraction, the P's cancel, leaving us N times F times 1. And if that 1 were any other number, we would have to write it in front of the NF, but it's a 1, so we don't. I guess you could if you wanted to, but it's assumed to be there. When you see a letter with no number in front of it, you can assume it's a 1. In the second fraction, the n's cancel, leaving me p times f. And in the third fraction, the f's cancel, leaving me p times n. So the good news is I got rid of all the fractions. So the problem is automatically better, or at least in a lot of people's perspectives. The bad news is the thing I'm solving for now shows up twice instead of once. So I traded in one problem for another. Well, we've already talked about how to fix this problem. It's what we did back here. To solve an equation for a variable that shows up more than once, get all the terms of the variable on one side of the equation, get all the other terms on the other side, factor out the common variable, and then divide. Well, the segregation move has already happened. Everything with an F is on the left, everything without an F is on the right. And the benefit of that segregation move, and please don't misread into my use of the word segregation. I'm using it in terms of what it means. It means to put things of one type over here, things of another type over there. I understand the negative connotation that word has had in the history of the United States, but segregating the F terms is technically the correct word to use here. All F terms on one side, non-F terms on the other. What that allows you to do is factor out an F as a common factor on the side that has all the F terms. Everybody gives up their F. We're leaving us with n plus p. We still have p times n on the right. But now notice that the only reason my F is not by itself is that it is multiplied by something, and I know how to get rid of things that are multiplied. I divide. It just so happens the thing it's multiplied by is an entire addition problem. So divide both sides by the entire addition problem, and we end up getting F equals a fraction with Pn on top and n plus p on the bottom. You know what can cancel in that fraction? Nothing. Because the parts in the denominator are parts of addition problems. You must be parts of multiplication problems if you're going to cancel in the fraction. And if you're thinking, wait a minute, didn't you split the fraction before? Like kind of, where'd it go? I know it's here. Here, when I made this move, I did, but I split it across the numerator, which is allowable because I unadded fractions and kept the common denominator. In this problem, the addition problem is in the denominator, and I can't split it. If you're going to split a big fraction into multiple fractions additively or subtractively, you can only split the numerator, not the denominator. There's not much I can do to simplify this, so that's going to be our final result. All right, I'm going to, like I said before, I'm going to try to make more instructional videos for the support content, the Math 0314. Because I don't have a set of videos already made for that. I got all the college algebra videos, obviously, but I'm going to try to do this each week. Have a support, not only the support assignment, but a video custom made by me to help you get through that particular assignment. If you have any questions, please text me. Please message me in Canvas. I'll be happy to talk with you.